In this video, I will be talking about atomic and ionic radius. Let's start with the definition. If we consider the atom as a sphere, the atomic radius is the distance of the outermost shell electron from the nucleus. The position of an electron cannot be measured exactly, and so the atomic radius also cannot be measured exactly if we are considering the position of the electrons. We measure the atomic radius as the distance between two nucleuses of two atoms held in a covalent bond and divide that distance by 2. We consider that distance as the atomic radius. And by that definition, we can have three types of atomic radius. We can have covalent radius for atoms that are held in a covalent bond. We can have metallic radius for metals, and we can have van der Waals radius for noble gases. How do you think atomic radius varies down the group? Now, before we go into how atomic radius varies down the group, we need to know about shielding. Shielding is the phenomena that restricts the attraction of the nucleus for the outermost shell electron. So here we have two atoms. And for the first atom, there is only one shell between the outermost shell electron and the nucleus. For the second atom, we have three shells between the outermost shell electron and the nucleus. And that's why for the second atom, it is much more difficult for the nucleus to attract the outermost shell, because the inner shells are continuously competing for the attraction for the nucleus. And that's why the attraction of the nucleus for the outermost shell for the second atom is considerably less than the attraction of the nucleus for the first atom. This phenomena that hampers the attraction of the outermost shell because of the inner shell, this is called shielding. Atomic radiuses increases down the group because of the following reasons. Number one reason is because the number of shells increases. So as we go down the group, for example, if we go down group 1, the number of shell increases from 2 shells in lithium, then we have 3 shells in sodium and 4 shells in potassium, and so on. And so as we go down the group, the increasing number of shells means the atomic radius also increases. And this also comes with increase in shielding. As we go down the group, the number of inner shell also increases, and as the number of inner shell increases, so does the shielding, and that is why atomic radius also increases. Because of reason 1 and 2, the attraction of the nucleus for the outermost shell decreases, and as a result, the nucleus is little more further away than it would have been, and so the atomic radius increases down the group. We can say that the atomic radius may decrease because of the increase in nuclear charge. As we go down the group, for example, as we go down group 1, the number of proton increases. So lithium has 3 protons, sodium has 11 protons, potassium has 19 protons. As we go down the group, the number of proton increases, and so we can say that because of the increasing number of proton, atomic radius may decrease, because the increased protons means more attraction for the outermost shell electrons. But the atomic radius actually will increase because the increase in attraction because of the increase in number of proton is not actually strong enough to overcome the effects of factors 1 and 2. And this is how a graph looks for an increase for atomic radiuses down the group. As you can see, atomic radius generally increases down the group. How do you think atomic radius varies across the period? Atomic radius decreases across the period. The reason is because, number 1, the nuclear charge increases. And as the nuclear charge increases, the attraction of the nucleus for the outermost shell electron increases. And number 2, shielding remains the same. As you can guess, across the period, the number of shell increases the same. For example, sodium has 3 shells, the same for magnesium, aluminium, silicon, and for all the atoms in period 3. So as we go from left to right of the periodic table, the nuclear charge increases, but the shielding by the inner shells remain the same, and that results in increased attraction for the outermost shell electron by the nucleus. And increased attraction means the atomic radius will decrease. So this diagram shows the comparative atomic radiuses for all the atoms in the periodic table. And as we can see, atomic radius increases down the group and atomic radiuses decreases across the period for the reasons we have just mentioned. If we plot the atomic radius for all the atoms of the periodic table from proton number 1 to proton number 20, then we see a graph like this. And we can see there are decreases in atomic radius, but there are also sudden increases in atomic radiuses. Now, notice that the sudden increases in atomic radius are when the period changes. For example, it occurs from helium to lithium because the period is changing from period 1 to 2, and so lithium has 2 shells. That means it will see a massive increase in atomic radius from helium to lithium. From another jump in atomic radius is from neon to sodium, and this is because neon has 2 shells but sodium has 3 shells, and you see a jump in atomic radius. And for the same reason, you also see a jump in atomic radius from argon to potassium. And in between, we see decrease in atomic radius, and that is because atomic radius is decreasing across the period from left to right of the periodic table. So from lithium to neon, we see a decrease in atomic radius, and we also see a decrease in atomic radius from sodium to argon. Ionic radius is the distance of the nucleus to the outermost shell electron of an ion. So for example, when sodium forms an ion, as it is a metal, sodium loses its outermost shell electron. And so its outermost shell vanishes when it forms the ion, and the distance of the nucleus to the outermost shell electron of the sodium ion is the ionic radius of the sodium ion. How do you think ionic radius varies down the group? Ionic radius increases down the group, and the ionic radius increases down the group for the same reasons as the atomic radius increases down the group. Understand that all the members of the same group forms ions in the same way. For example, all elements of group 1 produces ions by losing 1 electron from the outermost shell, and all elements of group 7 forms ions by gaining 1 electron in its outermost shell. And as we go down the group, the number of shell increases for the ions, the shielding remains the same, and as a result, the attraction of the nucleus for the outermost shell electron decreases. And the combined effect of all these three is that the outermost shell electron is further away from the nucleus, and as a result, ionic radius increases down the group. So this graph shows how ionic radius varies across the period. We can see that there is a decrease in ionic radius for the positive ions, and then there is a sudden increase in ionic radius, and then there is a decrease in ionic radius for the negative ions. Now, the reason why this change occurs is down to their electronic configuration. All the metals forms ions by losing 1 electron. All the metals forms ions by losing electrons from their outermost shell. And all the metals of the same period have the same electronic configuration. For example, sodium ion will have an electronic configuration of 2,8. Magnesium will have the same electronic configuration after losing 2 electrons from the outermost shell. Aluminium will have the same electronic configuration of 2,8 by losing out 3 electrons from the outermost shell, and so does silicon if it loses 4 electrons from the outermost shell. All of them have the same electronic configuration, but their proton number is increasing. And as we have seen previously, the electronic configuration is the same, and so the shielding is same, and as the proton number increases, ionic radius decreases initially from sodium to the silicon ion. But for the nonmetals, that is phosphorus, sulfur, and for the chloride ion, they gain electrons in their outermost shell. So they retain their third shell. And so all these three ions have one extra shell than the metal ions. And this is seen as a jump in the ionic radius from the silicon ion to the phosphorus ion. As we go from the silicon ion to the phosphide ion, there is an increase in ionic radius because the phosphide ion has one more shell than the silicon ion. And then we go from phosphorus to silicon, the ionic radius again decreases because all these three ions have the same electronic configuration, but their proton number is increasing, their nuclear charge is increasing, and greater attraction means the ionic radius again decreases. So there is two reasons for these three changes. The decreases across the period is because of increase in nuclear charge and the same electronic configuration and the same shielding, and the sudden increase in ionic radius is because there is an increase in one shell from the silicon ion to the phosphide ion. Now, before we move on to the next topic, we have to understand another idea, and that is called effective nuclear charge. Effective nuclear charge is the measure of how much attraction the nucleus has for the electron of the outermost shell. The nucleus of all atoms does not attract the electrons of the outermost shell with the same force. Some nucleuses attract the electron with much greater force, some with less force. Effective nuclear charge is a measure of the attraction of the nucleus of an atom or ion for the electrons in their outermost shell. Effective nuclear charge increases if an atom loses electrons. So for example, for a sodium atom, 11 protons are attracting 11 electrons. But when the sodium atom loses one electron, now it has a total of 10 electrons to attract. And so the 11 protons can attract these 10 electrons much more effectively than when the 11 protons were attracting 11 protons. And so the nucleus is effectively showing more attraction for the electrons. And so the effective nuclear charge increases whenever an atom forms positive ion. The opposite is true when an atom forms negative ion. For example, for an oxygen atom, 8 protons are attracting 8 electrons. An oxygen atom has equal number of protons and electrons, and in an oxygen atom, 8 protons are attracting 8 electrons. But whenever the oxygen atom forms an oxide ion, now the 8 protons are attracting 10 electrons. Oxygen gains 2 electrons in its outermost shell whenever it produces an ion, and so the same 8 protons now has to attract an increased number of electrons. 8 protons are now attracting 10 electrons. And so these 8 protons now has a more difficult time of attracting all the 10 electrons, and so the attraction of the nucleus for all the electrons is smaller, and so the effective nuclear charge decreases. And this explains the difference in atomic radius for atoms and ions. Whenever an atom forms a negative ion, the size of the negative ion is generally greater than the size of the atoms itself. For example, whenever an oxygen atom gains 2 electrons to form an oxide ion, its ionic radius will be greater, and the reason is because effective nuclear charge decreases because there are more electrons, and so the nucleus is not able to attract more effectively. And number 2 reason is because there is increased repulsion of the greater number of outermost shell electron. So when the oxygen had 6 electrons in the outermost shell, there were some amount of repulsion between the 6 outermost shell electrons and the inner electrons. But whenever it gains 2 electrons in the outermost shell, it has 8 electrons in the outermost shell, and there is increased repulsion between the electrons of the outermost shell, and so the ionic radius is also greater. Note that the shielding does not change. When an oxygen atom forms an oxide ion, we do not mention shielding because the number of shell has not increased. The radius of a positive ion is smaller than its parent atom. For example, the magnesium ion is smaller than the magnesium atom. And the reason is because effective nuclear charge increases. As the number of electrons has decreased, the 12 protons of the magnesium nucleus finds it easier to attract the 10 electrons of the magnesium ion. And so the effective nuclear charge has increased, and so the ionic radius is smaller, and also our shell has also decreased. Magnesium atom has 3 shells, 2, 8, 2. But whenever it loses the outermost shell 2 electrons, now it has 2 shells, 2 and 8. And so the shielding has decreased, and as a result, attraction also increases for the outermost shell. And so the shielding has decreased. And number 3, there is 1 less shell than the magnesium atom. And because of all these 3 factors, the ionic radius of a magnesium ion is smaller than that of the magnesium atom.